All right, today we are covering 8.2, which is on Venn diagrams. So if you haven't seen these before, these are really neat and kind of fun to work with. So Venn diagrams are a useful way of representing the events in a sample space. These diagrams usually consist of a rectangle, which represents the complete sample space U, and circles within it, which represent particular events. Venn diagrams can be used to solve certain types of probability questions and also to establish a number of probability laws. There's actually a lot more than what we're going to cover. You actually can in college take a full probability course. So if this interests you, that might be something when you're looking for electives. You could take a probability course in college. All right, the universal set or sample space U is represented by a rectangle, okay? So you have this rectangle. And a set within the universal set is usually represented by a circle. A prime, which is the shaded green part, is called the complement of A. So A prime is anything that's not in A. And something I think we looked at last time is that the probability of A plus the probability of A prime equals 1. And A prime is the complement of A. So you can call it A prime or the complement of A. And you'll hear me go back and forth between. So if U, let me change colors because it's fun to do. If U is the universal set, 1, 2, 3, 4, 5, 6, 7, and A is 2, 4, 6, watch what I'm going to do. I'm going to put 2, 4, and 6 inside of A. Then A prime, or the complement of A, is 1, 3, 5, 7. So those four numbers are outside set A, but somewhere in the rectangle. X is in A, or sometimes it's read X is an element of the set of A. N of A reads the number of elements in set A, so that is not new to us. A intersect B. Hopefully you saw this back in geometry. If not, we'll go at it as if you haven't. So this A, and it looks like an upside down U. B denotes the intersection. That means what do they have in common? So if you notice here, A intersect B is this shaded region in between. And A intersect B says X such that X is an element in A and X is an element of B. A union B denotes the union. That means it's all the elements belonging to either or the both, okay? Disjoint sets are sets that have nothing in common. So in this picture here, hopefully you can see this picture, they have nothing in common. There's nothing in an overlapped spot. So we would say these two sets are disjoint and A intersect B is the empty set. That means they have nothing in common, and A and B are said to be mutually exclusive. Okay, that means they have no common elements. All right, so let's take a look at an example where we can actually draw a Venn diagram. So it says in a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both of these subjects. Display this information on a Venn diagram. So we're going to start there. Now they have something in common, so I am going to have an overlap. And what I like to do is I like to start with the overlap and then work my way out. So, whoops, it says 15 students study both. Well, then in the P circle, I need 19. Well, I have 15 of them. So that means this part here, which is physics but not chemistry, there's 4 students. If chemistry has 17 and I have 15, that means there's 2 here. Now, I want you to add these up and tell me how many students out of the class of 30 don't study physics or chemistry. All right, well, you take 4 plus 15 plus 2, that's 21, and there's supposed to be 30 students, so it should be 9. All right, so now we want to find the probability, okay, not number of students, but we want to find the probability that a randomly selected class member studies both subjects. Well, both subjects is 15 out of the total, which is 30, so that would be 1/2. Studies physics but not chemistry. Well, a question I have for you is how many, oops, sorry, I'm on C, well, let's go down there. Study physics but not chemistry. So how many are in physics but not chemistry? Well, that's 4. So that reduces to 2 out of 15. All right, let me actually go to B. If they study at least one subject, one of these subjects, well, that's 4 plus 15 plus 2 out of 30, which is 21 over 10, or 7/10. All right, D. What's the probability they study exactly one of the subjects? Well, there are 4 students who do exactly physics and 2 that do exactly just chemistry. So that's 6 over 30, or 1/5. All right, last one. What is the probability that a randomly selected class member studies neither subject? Well, that's 9 out of 30, which is 3/10. All right, we have the addition law. For 2 events, A and B, the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B, which in other words means the probability of either A or B or both equals the probability of A plus the probability of B minus the probability of both A and B. So here's an example. If the probability of A is 0.6 and the probability of A union B is 0.7 and the probability of A intersect B is 0.3, find the probability of B. So I'm going to start with this addition law. And I'm going to plug in what I know. So the union is 0.7, probability of A is 0.6. I don't know the probability of B, that's what I'm looking for. And the probability of A intersect B is 0.3. So go ahead and solve that for me and tell me what you get. And I got the probability of B is 0.4. All right, last idea here. We already talked about this, but we're going to talk about it again. If A and B are mutually exclusive events, that means they have no overlap, they have nothing in common, then the probability of A intersect B is 0. So what that does is that takes the addition law up here and it makes the probability of A intersect B 0, so we can condense it to probability of A union B equals the probability of A plus the probability of B. I personally, I don't want one more thing to remember, so I stick with this one up here. Okay, let me use my pointer. I just stick with the addition law, and then I'm not going to worry about it. If your brain can hold more, great. My brain sometimes just cannot handle any more than it's already trying to handle. So here we go. Last example. A chocolate is randomly selected from a box which contains 6 chocolates with hard centers and 12 chocolates with soft centers. Let H be the event that a randomly selected chocolate from the box has a hard center, and S be the event that a randomly selected chocolate from the box has a soft center. Part A says, are the events mutually exclusive? Yes, because you can't have a hard center and a soft center. So then, what is the probability of getting a hard center? Well, there's 6 out of, well, if there's 6 plus 12, there's 18 total, so that's 1/3. The probability of getting a soft center would be 12 out of 18, and we reduce all our fractions. All right, and then what do you think the probability of getting a hard center intersect a soft center is? Well, they're mutually exclusive, so it's 0. And then the probability of getting a hard center or a soft center, well, you would take 6 plus 12 over 18. That's 1, or 100%. All right, so stop there. The extra practice we'll do in class together.